Welcome to CSI Training. Our mission is to impart the information, techniques, and confidence to successfully apply RBM, reliability-based maintenance technologies and products. Thank you for joining the thousands who have recognized and selected CSI Training as the world leader for quality instructional products. This program, Electric Motor Analysis, provides a solid foundation for analyzing electric motors by examining the physical construction of motors and the principles on which they operate. Here we demonstrate how to diagnose the electrical condition using vibration measurements, current measurements, and flux measurements, including the best setup for each. Case histories provide examples of all the measurements with specific instructions on how to determine the motor condition. Although we illustrate the physical construction of DC and synchronous AC motors, this program focuses on AC induction motors. First, let's take a look at the design and theory of electric motors to see how they operate. Motors are devices that convert electrical energy into mechanical rotating energy. They come in numerous shapes and sizes to meet specific power, speed, size, and environmental requirements. Motors are made up of two primary parts, the rotating part called the rotor and the stationary part called the stator. The rotor responds to an electromagnetic field in the stator, causing it to spin. AC induction motors have no electromechanical tie to the rotor. AC synchronous motors differ in that they have a mechanical tie through the use of slip rings to input a DC current to the rotor. The DC rotor or armature has either slip rings or a commutator. This program focuses on induction motors. The rotor itself is made up of rotor bars connected by end rings and a core. The core is made of individual soft iron laminations insulated from each other, which reduces the amount of eddy current traveling through the core and therefore reduces heat and increases efficiency. The end rings and bars can be cast onto the core as one piece using a material like aluminum, or they can be individual bars such as copper that are then connected to end rings. These bars and end rings carry the current and must have good connections. This type of rotor is usually referred to as a manufactured or fabricated rotor. The other part of the motor is the stator. It is assembled in the housing. Like the rotor, it has a core of electrically insulated soft iron laminations to reduce eddy current flowing through this core, which then reduces the amount of heat generated. The slots in the core are for coils. The coils are windings made up of individual insulated wires that are wound to the size to fit the core and with the proper number of windings or turns for the prescribed horsepower. They are then pressed into the slots in the core called stator slots with heat-resistant paper as additional insulation from the core. Notice how one side of the coil is pressed into the slot and the other side is then pressed into a slot along with another coil. The two coils are electrically insulated from each other with insulating paper. When all the coils are in place, the ends of the coils are connected to form the A, B, and C phase line leads for the motor. The ends are tied together to hold them in place, and the entire stator assembly is tested before being heated and then dipped into a varnish vat that insulates the individual components and stiffens the stator assembly. Another method sometimes used to insulate the stator is the VPI system. It is a vacuum pressure impregnation process using an epoxy or polyester resin mix that is heated. A vacuum is drawn to remove air and moisture. Then the stator is flooded with the resin, forcing it into the stator using pressure. The epoxy is baked on to all the surfaces, forming a rigid stator assembly. The stator assembly is still somewhat flexible though, because it is made of a thin soft iron laminations as the core, soft copper wire, paper, and varnish. It is assumed that during operation the stator does not move. However, this footage of a stator during startup was captured with a special camera that allows us to see any action in slow motion. Notice the flexing that occurs. This movement is at a frequency equal to 2 times line frequency. The air gap between the stator and the rotor must be the minimum distance that still allows for thermal expansion of the rotor and the flexing of the stator. Depending on the motor size, typical air gaps range from 25 thousandths of an inch to 100 thousandths. In very large motors, the air gap can be as much as 500 thousandths. Now that we've seen the components that make up a typical motor, let's take a look at the principles that cause a motor to work. Electric motors operate on the principle of magnetism. Although most motors do not have permanent magnets in them, they use electromagnetic fields to force the rotor to spin in much the same way that the fields of bar magnets can repel or attract each other. When wire is coiled around iron and current passes through the coil, the iron becomes a magnet. It can then be used like a permanent magnet. Each end of the magnet is called a pole. They are called the north and south poles. The same ends of two magnets repel each other and opposite ends attract. This repelling and attracting force is called the magnetic field and is strongest at the poles. The magnetic field is made up of individual lines called flux. In a motor, the coils are placed in the stator so that they wrap around a section of the laminated iron core. When voltage is applied, a magnetic field is produced, which is called an electromagnetic field. The strength of the field, or the force of the field, is dependent upon the number of wraps in the coil, the closeness of the wraps in the coil, the size of the coils, and the voltage applied to the coil. When a three-phase stator is connected to a three-phase source, three independent currents flow, one in each of the phase windings. These currents are displaced from each other by 120 electrical degrees. This 120-degree separation in time between the phase currents produces the stator's rotating field. The relative motion between the rotor and the stator causes the rotor bars to cut the stator's lines of flux. This induces a voltage on the rotor and causes current to flow, developing a magnetic field on the rotor. With the addition of the rotating field, all the requirements have been met to induce a voltage on the rotor, a current-carrying conductor, the rotor, a magnetic field, the stator, and relative motion between the two, the three-phase power. The stator's and rotor's magnetic fields interact based on the principles of magnetism, causing the rotor to spin. The difference between the revolving field speed and the rotor speed is called slip. When the rotor is running near the speed of the revolving field of the stator, very little voltage is induced in the rotor, meaning that it is drawing very little power from the stator and therefore has low torque. To increase torque, there must be a greater amount of relative motion between the rotor and the revolving field. This is why an increase in load causes the stator to draw more current. Electrical defects in motors are either in the rotor or stator, and are most commonly a mechanical defect that adversely affects the electromagnetic field or flux. In a fabricated rotor, the most common problems are at the joints where the rotor bars join the end rings. These joints may become loose, causing opens or high-resistance connections, which restrict the current flow, causing the flux to be less for that rotor bar. The reduced flux causes changes in rotor speed as the open area passes the stator poles. The open also generates heat. The excessive heat causes the rotor to expand at that location, resulting in an unbalanced condition. The heat also causes the rotor to grow axially, putting additional force on the bearings, accelerating their degradation. The rotor bars can develop cracks or even break in two. Since the rotor bars carry current to the end ring and to another bar, the crack or break affects more than just one bar. Since it is not carrying its load, it causes small changes in the rotor speed as these bars pass the stator poles. The adjacent rotor bars run hotter due to the increased current flow. It is similar to the effect that can be seen with infrared thermography of a power cable that has a broken strand. Since it does not carry its load, the other strands run hotter. When several rotor bars are broken, the motor constantly pulses as it changes speed, adding vibration to the system. The end ring can develop defects such as cracks, since the current moves along a rotor bar to the end ring and then along the end ring to a rotor bar on the other side of the rotor. Cracks cause increased resistance to current flow. Excessive heat is generated with any open or high resistance spot, and when these are on the end rings, the heat tends to cause the rotor to expand axially as well as radially, exerting force against the bearings, accelerating bearing degradation. A cast rotor has the same characteristics as a fabricated rotor when a fault is present on either the rotor bars or the end rings. However, aluminum is a porous material, meaning that it has minute voids throughout, causing it to have higher resistance and run hotter. Shorts between laminations and large voids also cause more resistance and increase heat. A clue to a casting having large voids is there will usually be a large number of balance weights concentrated in one area. The heat breaks down the insulation on the stator windings, shortening motor life. Let's take a look at the problems that can develop in the stator. The most common problem is insulation breakdown due to excessive heat. The single most important parameter influencing the reliability of electric motors is insulation, and the single biggest enemy to insulation life is heat. In fact, for every 10 degrees Celsius rise above the nameplate temperature rating, the winding life is reduced by half. The high temperatures can be a result of blocked cooling fins on the housing, a dirty environment allowing dust and dirt to accumulate in the windings, excessive loads, excessive eddy currents or core losses from shorts between laminations, or from open rotor bars or stator shorts. Insulation breakdown causes shorts from turn to turn in a winding, from phase to phase, or a short to ground. A study by GE on the cause of motor failure showed that nearly 60% of the failures were due to turn shorts. Phase-to-phase shorts accounted for just over 20%, and shorts to ground accounted for the rest. Recall that in each stator slot there are 2 coils, and in a 3-phase motor the coils are from different phase legs. So if the insulation breaks down between the windings, it could short from one phase to another, which reduces the total flux and therefore the motor's power. Insulation breakdown may cause a short from phase to ground, causing flux losses. Poorly designed stators will generate a pulse at the stator slot frequency due to the changes in the flux fields. This pulsing adds real vibration to the system, accelerating bearing degradation and shortening motor life. To have a uniform magnetic field or flux field, the air gap must be uniform. Any uneven air gap is called eccentricity. There are several conditions that cause an eccentric air gap. If the center of the rotor is not in line with the center of its shaft, it will cause the air gap to be eccentric. Since the eccentric air gap changes positions as the rotor turns, this condition is called dynamic eccentricity. Both ends of the shaft must be concentric with the rotor, or the resultant air gap will be eccentric. If the rotor has open rotor bars that generate heat, the rotor will expand at that point, causing it to be eccentric and generate dynamic eccentricity. Another eccentric air gap condition can exist, and it is static eccentricity. Static eccentricity is a condition when the air gap is eccentric, but it stays in the same position. This can result from 2 causes. One is that the center line of a perfectly round rotor is not in line with the center line of a perfectly round stator, or it is off-centered. The second cause is the rotor may be perfectly round, but the stator is oblong, so that there is more gap on 2 sides of the rotor than the other 2 sides. In both dynamic and static eccentricity, the electromagnetic fields are not uniform, causing the rotor to constantly adjust speed, generating a pulsing vibration. With dynamic eccentricity, the eccentric rotor may be unbalanced and therefore exhibit characteristics of unbalance as well as the pulsing due to uneven flux. Let's take a look at traditional measurements used to detect some of these problems. Traditional tests require that the motor be taken offline and the power supply lines be disconnected from the motor. and these tests can only detect stator problems. 3 tests are commonly used. They are a surge test, a Megger test, and a high-pot test. The high-pot test detects insulation breakdown that cause phase-to-ground shorts and shorts from phase to phase. The connections are made to a frame ground and to each phase leg. Voltage is applied across the phases with very low amperage to check for leakage. As the voltage is slowly brought up to about double the operating voltage, leakage will occur as the unit initially acts as a capacitor. After the desired voltage is reached, in this case 9600 volts, it is held for a minute or so to determine if there is any current leakage. The unit should have linear leakage and no shorts after reaching this level. Each phase must be tested in the same manner. The surge test detects insulation breakdown, shorts to ground, and shorts turn to turn. It does this by comparing the response of 2 phases at a time when a rapid pulsing voltage is input. When no winding problems exist, the 2 signatures should be the same. When a short exists, the signature is damped. The Megger test uses a megohm meter and is similar to the high-pot test. It applies a DC voltage to check phase-to-phase and phase-to-ground insulation condition, and these resistance values can be trended. The next section shows the test and measurements that can be made without taking the machine offline. RBM tests and measurements can be made to determine the electrical conditions of the motor without taking the motor offline. These include vibration measurements, electric current measurements, flux measurements, and temperature measurements. There are some terms you must know in diagnosing electrical conditions. One is slip frequency. Slip frequency is the difference between the synchronous speed and the actual turning speed. For example, a synchronous speed of a 4-pole motor is 30 Hertz, or 1800 cycles per minute. However, the actual shaft turning speed may only be 29.5 Hertz, or 1770 RPM. The difference is a half Hertz, or 30 cycles per minute, and is called the slip frequency. This slip frequency is a key in locating sidebands in spectral data. Other terms are slot pass frequency and rotor bar frequency. Slot pass frequency is the number of slots on the stator that a point on the rotor will pass in 1 shaft revolution times shaft speed. It is equal to shaft turning speed times the number of stator slots. Slot pass frequency will always be divisible by 3 since there are 3 phases. Rotor bar frequency is the number of rotor bars that pass a point on the stator in 1 shaft revolution times shaft speed. It is equal to shaft turning speed times the number of rotor bars. Since defects in the motor affect the flux, the rotor changes speeds as it moves through changes in the flux. These speed changes cause pulses, which are a mechanical vibration and can be measured with vibration sensors. Here we show how and where electrically related problems show up in vibration data. Vibration measurements made during normal routine data collection can provide an indicator of the motor's electrical condition, and they can indicate the rotor condition, the stator condition, and both dynamic and static eccentricity. However, traditional parameter sets will not detect most electrical problems. This is because the maximum frequency may be set too low and the resolution is not high enough. Electrical defects show up in 3 frequency regions of the spectrum. One region is a high frequency equal to the number of stator slots and the number of rotor slots. Another region is the opposite end of the spectrum around the 1 times turning speed peak. The third region is the area around 2 times line frequency. In the region around the 1 times peak and the region around 2 times line frequency, the key to determining an electrical defect is the spacing and amplitude of any sidebands. In normal routine vibration data, the resolution is not adequate to see these sidebands because typical resolution is only about 1.5 Hertz. These sidebands are usually less than 1 Hertz and can be as close as 1/10 of a Hertz. Rotor defects, such as broken or cracked rotor bars, will show up in the vibration spectrum at rotor bar frequency and will have sidebands spaced at 2 times line frequency, or 120 hertz. However, the predominant location in spectral data is the 1 times turning speed peak, which looks like unbalance. This is because the rotor actually is unbalanced due to thermal growth as extra current is carried by adjacent rotor bars. This turning speed peak, though, will have sidebands. The sideband spacing will be equal to the number of poles in the motor times the slip frequency. If the time waveform is monitored and the power is shut off, the energy due to the electrical defect will drop out, leaving the unbalanced sine wave. Stator problems show up at 2 times line frequency. However, stator problems such as shorts from turn to turn, winding to winding, and phase to phase have a very short life, and the motor will usually trip a breaker or fail before vibration measurements can be made. Other stator problems such as eccentricity, poor winding quality, and misaligned coils affect the flux field and generate a pulse at 2 times line frequency. Amplitudes at this frequency should not exceed 0.1 inches per second in general use 50 to 1,000 horsepower motors. If the motor is used in a machining process, the amplitude at 2 times line frequency should be less than 0.025 inches per second. In the case of eccentricity, the vibration may be very directional. In static eccentricity, the flux is strongest where the rotor and stator are closest, and weakest where they are the greatest distance apart. During one rotation, the rotor passes through the strongest field and the weakest field, causing pulsing and therefore high vibration. For this reason, the peak at 2 times line frequency could be very directional. It would have the highest amplitude in the direction of the eccentricity and much lower in the direction where the air gap is equal on both sides of the rotor. To capture these problems in vibration data, 2 considerations are required. First, the motor should be running at full load or at least 50% load. Without a full load, the stresses are minimized and problems are masked. Secondly, special setups are needed. The sensor should be an accelerometer with the sensor power on. Collect 2 averages with 1600 or 3200 lines of resolution and a maximum frequency of 130 hertz. This captures the sidebanding around 1 times turning speed and the area around 2 times line frequency. Collect another spectrum to slot pass frequency plus 6 times line frequency. Use 4 averages with 3200 lines of resolution. This shows only sidebanding around either rotor bar frequency or slot pass frequency. The amplitude in this frequency range should not exceed 0.06 inches per second. However, it is always best to trend this peak for any change. The amplitude can be stable at 0.1 inches per second, indicating it may not be degrading electrically, but the vibration is very real, accelerating mechanical failure. Keep in mind that the rotor bar pass and stator slot pass frequencies may be in the resonance range of handheld transducers, and therefore the amplitude will be magnified. Be sure to use the accelerometer and mounting technique that provide an accurate amplitude in this frequency range. After detecting the possible electrical problem in vibration data, follow up with current measurements to confirm the findings and determine the severity. An analyzer and a handheld current clamp as the sensor are used for electrical current measurements to determine rotor condition. The recommended settings for collecting current data are provided at the end of this section. These measurements are high-resolution measurements around line frequency to analyze the sidebands. The vibration measurements looked at the rotor movement or turning speed multiples with sidebands of the pulses modulating the turning speed. The current measurements ignore the vibration, but look at the electrical current at line frequency and its sidebands. The best amplitude units for a current spectrum are dB amps. This is because the amplitude relationship between the line frequency peak and the sidebands can be so great that the sidebands are not discernible in a linear scale. This spectrum is of current data displayed on a linear scale. Notice how the sidebands are negligible in amplitude. However, the same data displayed in a log scale brings the sideband amplitude out of the floor of the spectrum. Now the amplitude of the line frequency peak can be compared to the sidebands, which are spaced at slip frequency times the number of poles. The amplitude difference is referred to as dB down. For example, the sidebands are less than 40 dB down. The rules of thumb for analysis are: if the slip frequency times the number of pole sidebands are greater than 54 dB down, the rotor is okay. If the sidebands are 45 to 54 dB down, there are high resistance joints, such as casting flaws or a cracked rotor bar. A difference of 40 to 45 dB down indicates at least one broken rotor bar. If the motor is not subjected to frequent starts or excessive load, it may run in this condition a long time. Continue to collect this reading and trend it for a change. When the dB down is 35 to 40 dB, there are multiple broken bars or multiple high resistance joints. Plan on working on this motor soon. 30 to 35 dB down indicates there are several broken rotor bars or an end ring is broken. Schedule the replacement, or it will schedule you. If the sidebands are less than 30 dB down, there are multiple problems in the rotor, and it should be taken offline immediately and repaired. Remember that these current measurements detect the rotor condition and not the stator condition. A case history of a 1500 horsepower motor illustrates how current and vibration measurements work hand in hand to detect electrical problems. The motor is a two-pole motor with an actual turning speed of 3,558 RPM or 59.31 Hertz. This means the slip frequency is about 0.69 Hertz. The vibration at 1 times turning speed was higher than normal, so additional high-resolution data was collected. The frequency range was set to 400 Hertz with 3,200 lines of resolution. This resolution separated the sidebands from the turning speed peak. There are 5 discrete sidebands to each side of the turning speed peak. They are separated by 1.3 Hertz, which is 2 times the slip frequency. It shows up at 2 times slip frequency because it is a two-pole motor. The motor has 34 rotor bars, so high-resolution data was collected around rotor bar pass frequency. There are several peaks around 34 orders that are spaced 120 Hertz apart. These are sidebands spaced at 2 times line frequency. A rotor bar problem was suspected. To confirm the diagnosis, a current measurement was collected. The amplitude at line frequency is 60 amps, and the sideband amplitude is 26.6 amps. This makes a dB down of 33.4 amps. Based on our rules of thumb for the probability of broken rotor bars, there are probably several broken rotor bars. When the rotor was disassembled, the silver solder had melted out from 12 joints where the rotor bars join the end rings. Excessive heat had caused the joints to fail. This is common in motors that must be started frequently because the load and heat generated are greatest during startup. To maximize these current measurements in an RBM program, the current measurement should be used in a similar way that vibration measurements are used. That is, collect one reading when the unit is put into service to use as a reference. Then continue to collect vibration data and trend it for changes. When changes are detected in vibration data, collect another current spectrum and check for rotor bar problems. Since these current measurements require the presence of an electrician to open the cabinet, collecting them only when a problem is suspected saves time and money. Capitalizing on these current measurements requires special setup. The measurement point should be set up with a maximum frequency of only 80 Hertz, with 3,200 lines of resolution and 4 averages. With this high resolution, the data could take 1.5 to 2 minutes to collect. The collection time depends on the processing speed of the analyzer. The averaging mode is set to normal with a Henning window. The sensor type is a current transformer, and since it is supplying its own power, no power should be supplied to it from the analyzer. Remember, the current data collected to 80 Hertz is not used to detect stator problems, but is used to identify rotor-related defects. Another application for current measurements is checking the phase balance. All 3 phases of the power supply should be equal or balanced. If they are not equal, for example 60 amps, and 50 amps, It indicates either a problem in the line power or a problem in a phase winding of the motor. To make these measurements, use a similar setup as before, except with one change. Since we are only looking for a total current draw out to 80 Hertz and are not concerned with sidebands, the resolution can be set to 100 lines. This shortens the collection time, making these measurements quick. All other settings are the same as used for the current analysis measurement. If you have made one high-resolution measurement on a phase leg, another low-resolution spectrum is not required for that leg. For safety, we recommend that current measurements be made at the CT or current transformer rather than the actual phase line. Never exceed the safe voltage limits for the current clamp, which is usually rated at 600 volts. Follow all safety guidelines for collecting this data. Once baseline current data is collected, you can make other measurements which provide the same information and more without having to access an electrical cabinet. These are flux measurements and are discussed in the next section. A growing technology uses a flux coil to capitalize on the flux field the motor generates while it is running. Since the uniformity of the flux field is directly related to the electrical condition of the motor, a spectrum of the flux can be used to detect problems in the rotor and the stator. There are benefits to flux data. It can be collected on a routine basis along with vibration data because no additional personnel such as an electrician are needed for opening cabinets. Flux measurements are made directly on the outboard end of a motor. Since the flux coil has magnetic feet, it can be placed on the end bell of most motors. This measurement depends on the flux field, so small changes in the motor flux affect the resulting data, and small changes in the coil position also affect the data. It is imperative that the coil be placed in the same position each time the measurement is made. Mark the feet positions with a paint marker or mount discs for the magnets. Two measurements are normally made. One is a high-resolution, low-frequency spectrum to look for rotor, stator, and phase unbalance problems. The second measurement is a higher frequency range to look at stator problems around slot pass frequency. Specific measurement point settings are given at the end of the section. The spectral data from a flux coil measurement will be much busier than data collected with a current clamp. This is due to the multiple and varying sources of flux that are generated. This data is from a 10-pole FD fan motor with a turning speed of about 711 RPM or 11.85 Hertz. Its slip frequency is 0.15 Hertz. One characteristic of flux data is the families of peaks that are evenly spaced around the line frequency peak. The line frequency peak at 60 Hertz has the same characteristics as current data. That is, it has sidebands spaced at the number of poles times the slip frequency. And the same criteria are used to determine rotor bar condition, the amplitude difference between the sideband and the line frequency peak. Current data collected the same day looks very different at first glance. The dB down values will be very different in the current and flux spectra. However, a change of 1 dB down in current will be paralleled by a 1 dB down change in flux. So in reality, they are both telling the same story. There is a rotor bar problem. But the flux spectrum can provide information about the stator condition. Let's take a closer look at the families of peaks. The sideband markers mark the families at a spacing of 11.86 Hertz or motor turning speed. The spacing of the peaks within the families is 0.7 Hertz, which is equal to half the number of poles times the slip frequency. A change in the trend values of these families of peaks indicates a problem in the stator. It could be turn-to-turn shorts or any other stator problems. If the amplitudes stay right there over several measurement periods, the stator is okay. Changes in the stator will show up in these families of peaks spaced at turning speed around line frequency. Stator anomalies also show up in the frequency range surrounding the principal slot pass frequency. Sidebands are spaced at 2 times line frequency. Present research indicates that a significant amplitude increase in these sidebands correlates to degradation occurring in the stator. The measurement point setups for these flux coil measurements require a high resolution of at least 3,200 lines. The low-frequency measurement around line frequency requires a maximum frequency equal to 3 times turning speed plus line frequency, or 2 times line frequency, whichever is greater. Use 4 averages in the normal averaging mode. Use a Hanning window and define the sensor as a flux coil. Do not provide sensor power since the coil generates a voltage from the motor flux. The high-frequency measurement should have a maximum frequency of slot pass frequency plus 15 times line frequency. This allows up to 7 harmonics of the 2 times line frequency sidebands to be included on the upper side. All other settings are the same as for the low-frequency point. Collect routine flux measurements along with vibration data and trend them for a change. When a change is seen, collect a current spectrum to verify the readings. Since flux data can be collected without special restrictions, such as needing an electrician to open a cabinet, use it as the first line of defense. These measurements can be analyzed one by one, or the analysis can be performed by a computer software program, such as CSI's MotorView 2, which automatically scans the data for families of peaks, individual peaks, and sidebands, as well as the loads on the motor. The software performs the analysis calculations and generates a report estimating the rotor and stator condition along with recommended actions. Heat is an enemy of electric motors, damaging the insulation and the bearings. Routine temperature measurements at 7 precise locations can help you spot overheating and detect motor problems before they do serious damage. Many conditions can cause overheating, such as restricted ventilation, single phasing, high ambient temperatures, excessive duty cycles, power supply variations, bearing seizure, and misalignment. Temperature measurements should be acquired when the motor is in a steady state condition. CSI recommends 7 locations for these measurements. 3 are surface or skin temperatures, plus 1 on each bearing, 1 at the center of the termination box, and 1 at the hottest spot on the coupling. Since we are looking for indications of electrical and mechanical failure with these measurements, the temperatures must be normalized, removing the effects of ambient temperature and load. An equation used to calculate the normalized temperature subtracts ambient temperature from the measured temperature and divides it by the percent load the motor is running. This number is then multiplied by 100 to yield the normalized temperature. Ambient air temperature is measured on the inboard foot of the motor, and the load is the percent of full load at the time the measurement is made. This trend plot shows the relationship between the motor speed and load and the effect of ambient temperatures. Notice how load and speed are exactly opposite. When the temperature measurements are normalized and trended over time, potential problems can be found and corrected. This trend plot covers 5 readings over 4 months. The temperature climbed steadily from May through July. After the July measurements were collected, the motor was inspected for airflow. It was found to be restricted due to buildup and was cleaned. The August measurements show the improvements in running temperatures and point to the benefit of tracking these measurements. These temperature measurements provide a quick method for determining excessive heat and can be used to detect and remove the leading cause of motor failure, excessive heat. The measurements can be normalized automatically when used in conjunction with MotorView 2 software, which also performs the analysis and generates a report for recommended action, saving you time and money. RBM measurements can be used for special applications that enhance your troubleshooting skills. Here we show how to use 2 techniques to provide answers to electrically related problems. The first technique uses vibration measurements, and another uses current measurements. This case history involves a 2-pole 60 horsepower motor driving a pump. The motor had high vibration of 0.8 inches per second at what appeared to be 2 times turning speed. One analyst assumed it was misalignment and checked it by uncoupling the motor. The peak at that frequency remained at 0.8 inches per second. A CSI analyst was called in to determine the problem. Based on this information provided and the knowledge of 4 characteristics of motors, he was able to confirm the real problem in just a few minutes. The 4 characteristics that he used to arrive at a solution are: 1. Since the peak did not move in frequency after the motor was uncoupled, it probably was not speed related. 2. The previous data had a resolution of about 1 Hertz and therefore could not differentiate the 2 times peak from 2 times line frequency. 3. Stator problems are indicated by a peak at 2 times line frequency. And 4. Since the stator is flexible and is tied to the housing, it could be distorted, generating a peak at 2 times line frequency. The analyst collected a high-resolution spectrum and found that the running speed was 59.92 Hertz, and the problem peak was exactly 120 Hertz, or 2 times line frequency, not 2 times turning speed. Therefore, it is definitely an electrical problem in the motor. But before sending it to the shop, another check should be made to verify the cause. Using the same high-resolution settings, the analyzer was put in the monitoring mode to monitor the peak. Then 1 foot on the motor was loosened a half a turn. The peak dropped to 0.08 inches a second. When the base plate was checked, it was 90 thousandths out. This so-called electrical problem was essentially a soft foot problem that twisted the stator, causing the 2 times line frequency peak. A soft foot problem is very common in motors up to 250 horsepower. It occurs in larger motors, but the stiffness of larger motors minimizes this occurrence. Because the analyst knew how to check for this, he saved the company the cost of a motor rebuild. A current measurement can be used to capture the current inrush during startup. This waveform data provides the starting current amperage, the amount of time the current was drawn, and the amount of time until operating speed was reached. Place the current clamp on the line lead or at the switchgear CT. The setup for this measurement uses a maximum frequency of 200 Hertz with 400 lines of resolution. Only 1 average is used. The averaging mode is normal, and the full-scale range is set to 5 times full load amps. The window is hanging, and the sensor is the current transformer. Trigger is set to pre-trigger of 35% and a trigger level of 5. The waveform display units will be in RMS amps. Accept these settings and begin collecting data. When the analyzer displays a no trigger message, start the